So it's basically those things. And specifically, those atoms have electrons, okay? Those atoms have electrons. And it turns out that when you squeeze electrons this close together, something weird starts to happen, okay? Something weird starts to happen. Specifically, there's a rule in quantum physics that tells us that electrons hate each other. Electrons absolutely hate each other when they get really close, okay? And I don't mean it's because they both have the same charge and the electromagnetic force like we talked about a long time ago. It has nothing to do with charge. Electrons just really hate other electrons when you squish them real close, okay? To the point where if you try to squish them right up on each other, they're gonna fight you, okay? Now, let me give you guys a metaphor. Let's just to show you the difference in the electrons. Check this out. Imagine we were in space, okay? Imagine we were in space. Whoa. And I was carrying around a whole ton of baseballs, like a million baseballs. I was carrying them around, and then all of a sudden, I trip on an asteroid. I don't know. I run into something, and oh no, I lost all my baseballs. Whoa. And they're just flying around. And I hire you guys to go get my baseballs, okay? Bring my baseballs, clump them together, squeeze them together, bring me them back. Don't overthink this. If you went out and captured all my baseballs and squished them all together, what are you going to have now? Don't overthink this. If you captured all my baseballs and squeezed them together tight, what are you going to have at that point? It's a weird metaphor, but yeah, you're just gonna have a big old ball of baseballs, right? You're gonna have a bunch of baseballs just squished together. You'll have one big old ball of baseballs, okay? Here's a question. Will those baseballs be touching each other? Probably. If you were to squeeze them together tight, are they probably going to touch each other? Yes or no? Yeah. They're all going to be touching. Each baseball will be touching a bunch of baseballs. I mean, there'll be some empty space where they don't quite, there'll be some empty spaces in there, but they will be touching, right? You wouldn't be able to take your hand and just squeeze them between the baseballs. Like, you'd run into baseballs, no matter what, right? Okay, now, let's say we did the exact same thing, but with a whole ton of electrons, okay? Oh no, I tripped and I dropped all my electrons. And I hired you guys to squeeze my electrons together, okay? Now, if you do that, if it was exactly the same as the baseballs, then you would have just a big old ball of electrons, right? You just have a big old ball of electrons just squeezed together, and they'd be touching, just like the baseballs, right? But that would not happen that would not happen with the electrons. Okay, if you guys tried to squeeze those electrons together, if you just crunch, they would come closer and closer together just like the baseballs did. But once they got really close, like closer than we're typically talking about electrons being normally, they would eventually see each other and be like, wow, no, that's another electron. I hate it. I hate these guys. I know I'm an electron, but I hate them all. I hate these guys so much. And so, if they really hate each other, if there's this intrinsic need to get away from each other, if you keep squeezing them, will they touch? Will they touch each other? If you can see where I'm going with this, yes or no? Are they going to end up touching? That's right. No, they're not going to touch, right? That's right. No, they're not going to touch each other. But if you keep squeezing, because gravity keeps on squeezing this white dwarf, that means that what's going to happen is that the electrons, because of the power of their hate, will end up gridding up. And the grid, basically, they're all going to get really close to each other as you squeeze them, and then at a certain point, they're going to stop getting any closer together. They will just resist your crush. And, I mean, the grid won't necessarily look exactly like this, but the important part is it forms a grid of electrons powered by the hate of the electrons. And there's a name for this, okay? There's a name for this. Electrons, they're like self-discriminating against each other. It's like self-discrimination of electrons. That's not the technical name for it, though. What's the technical name for what happens to the electrons when they get like this, when they get all hatey? They're called degenerate electrons. Somebody said introverts. This is a little worse. These guys are called degenerate. These degenerates can't even get along. So what is fighting gravity in a white dwarf? What keeps the white dwarf from just crushing forever and just keep on getting smaller and smaller? It's degenerate electrons doing it. When the electrons get degenerate, they fight the gravity. And so we say that these electrons are fighting gravity with electron degeneracy. Degeneracy. That's an E right there, I'm sorry. Degeneracy pressure. Electron degeneracy pressure is what supports the white dwarf's size, keeps it from crushing any smaller than the Earth, okay? Now, so basically you can think of a white dwarf as a giant Earth-sized grid of degenerate electrons with a bunch of hydrogen, helium, carbon, and oxygen atoms inside. And check this out. There's no more fusion in this white dwarf. And the fusion was the source of light and heat. So what will gradually happen to the white dwarf over time if the fusion is completely off? If there's no more fusion at all, what gradually happens to the white dwarf over time? Good one. What's going to gradually happen if the source of light and heat has stopped? Yeah, it's going to get gradually cooler and dimmer over time. The white dwarf's going to be able to hold on to its heat for a long time. So it'll stay hot and white for a long time. But over time, over millions of years, it gradually loses that heat. And the reason I wanted to bring that up is something that I think is kind of cool. Think about this. If this thing gradually cools down, then the carbon atoms inside will gradually start to turn into solid, okay? They will solidify. So this white dwarf will gradually develop a solid inside, deep down towards the middle, okay? And it will be made out of carbon, okay? And as time goes by, the gravity is going to continue to crush the carbon, okay? The electrons, they won't crush any closer together, but the carbon will get crushed. And do you guys remember what you make when you take solid carbon and you crush it extremely tight? There's a special kind of substance you get that's pretty cool and pretty valuable. See if you guys remember this. It's been a while since I mentioned it. What do you get when you crush carbon under intense pressure? Diamonds. Diamonds. So, over time, inside of a white dwarf, at least some of them, will produce enormous, bigger than city-sized diamonds inside. Okay? Diamonds. That's some bank inside of a white dwarf. So maybe one day our sun will have a giant diamond inside. Now, check this out. Check this out. Would you want to visit a white dwarf to go harvest that diamond? Would that be a good idea? Yes or no? And we're assuming you brought, like, oxygen tanks to breathe and all that kind of stuff. No, don't, we will never, I'm going to go ahead and wager to say we will never go try to harvest a diamond out of a white dwarf, okay? For one important reason. What's going to kill you if you try to visit a white dwarf? Let's see if we can figure that out. And I'm going to turn my page here. If you were to go try to visit a white dwarf, what might happen? A lot of things can kill you, but it's the gravity you gotta watch out for, okay? It's the gravity you gotta watch out for, okay? Because there's something weird going on, and this is going to be relevant when we talk about the other kinds of dead stars. Check this out. Let's say that this was a star, okay? It has a certain amount of mass to it, so it has a certain amount of gravity, right? And let's say that this was a low-mass star like our sun, so it dies and becomes a white dwarf. Most of that mass will leave, okay? Most of that mass will leave, and the only thing left over will be the leftover part that becomes the white dwarf in the middle, okay? So if you're way out here, if most of the mass of that star left, what's going to happen to the amount of gravity you feel from the leftover stuff? If most of the mass left, what's going to happen to the gravity you feel from the leftover core? Will you feel more gravity or less gravity from it? Remember, when this star dies, it releases and gets rid of most of its mass. You would feel less gravity from that white dwarf if you are far away. Okay? So, if you were at the distance of Earth, away from this star, so like that kind of distance, and it turned into a white dwarf, you would feel less gravity from it. But, check this out. Remember, if you go closer to an object, what happens to the amount of gravity you feel from it? If you go closer to it, what happens to the amount of gravity you're going to feel? More or less? It'll be greater, right? It'll be more. It'll be more gravity. It'll be more gravity. And so if you went even closer, you'd feel more gravity, right? And eventually, though, let's say it was the original star. If the original star was there, you'd run into the surface of that star. And let's pretend you don't die from that. At that point, that would be the maximum amount of gravity you could feel from the original star. Because it turns out, check this out, here we go. If the amount of gravity you feel from an object depends on the amount of mass between the center and you. So if you went inside of this star, some of the mass would be behind you, and that would not contribute to the gravity that you feel. So essentially, the maximum gravity you feel from a planet or a star is right at the surface level. If you go under the surface, you're going to lose some of the gravity as you go down, okay? But check this out. Because the white dwarf didn't have fusion, we said that gravity crushed it to the extreme. So that means that little tiny leftover core, once this stuff goes away, once this stuff leaves, this tiny core is crushed extremely tight. And you can go now closer to the center without getting... Lost my words. Give me a sec. Here we go. If you go towards just the white dwarf, here we go. Let me just do a different picture. If you go towards just the white dwarf, because it is crushed so small, you can now get closer to where the center is and still have all of the stuff in front of you. And so essentially all of what I'm trying to say is this. What I'm going to try to say is this, is you will feel more gravity from the white dwarf close to its surface than you did to the original star because the white dwarf is packed tighter, okay? When something gets packed tight, the gravity you feel from really far away isn't really affected, but the gravity you feel on the surface goes up the tighter it is packed. So because the white dwarf is so extremely packed, you're going to feel an extreme amount of gravity near the surface of that white dwarf. So yes, sorry to get your hopes up. We're not getting that diamond. How bad is it? Well, let's say that this was the surface of the white dwarf. If you were to somehow come down and land on this, first of all, the gravity will be so high that you will weigh millions of tons. You'll weigh millions of tons. And can your body support the weight of millions of tons? Quick yes or no. Do you even lift? No. No, you can't. Nobody can hold that much weight. So your own weight will crush you to death. If you tried to get close to a white dwarf. And even if you could somehow survive, if you would have to dig your way down through the electrons to get to the diamond stuff, carbon is denser, carbon's heavier, so it's gone towards the middle. So you'd have to dig your way down, and like one handful of these degenerate electrons is easily going to weigh again, thousands of tons, right? Thousands and thousands of tons in every handful. So it's going to be almost impossible to deal with. Also, while we're at it, the gravity here would be strong enough that your own weight would liquefy your body. Your body would liquefy under its own weight, okay? And your liquid would be able to seep between these electrons and get pulled towards the center of the star. So guess what? Juice You will get to go visit the diamond. Juice You gets to visit the diamond. Yay! But then what would happen to your juice when it got to the diamond? Can you guess what would happen? Here's a hint. There's a lot of carbon in your body. Guess what will happen to you once you get down there? Yeah. Yeah. Somebody said a blood diamond. That's not technically what that means. But yeah, you are the diamond now. You get to join the diamond in the center of the white dwarf, in a way. Yay! So don't go do it. It's probably not a good idea.